Welcome to the program, Dr. Özel.
Very nice to be here. Thank you.
A neutron star weighs so much. Why is a neutron star so heavy?
Because it's very dense. Because it's the remnant of a star that has consumed all its fuel. A star much, much bigger than our sun that at the end of its lifetime has collapsed a tiny object the size of Manhattan Island.
The whole star collapses to the size of Manhattan Island?
That's right. That's why it weighs so much and it's extremely dense.
And so how big do they start out before they do that collapse?
1,000,000 miles radius, for example, our sun. The stars that we're talking about are even bigger.
Wow. So you could fit a lot of our stars, our sun, inside those neutron stars.
When they are active as stars, that's right. But when they actually become a neutron star, they're one of the smallest objects that the universe creates, the densest and the smallest.
Give me the life history of a neutron star from the time it's a regular star till the time it collapses. What happens?
Well, what happens is it goes through its life as a fuel-burning, fusion-powered star at first, like our sun, like many other stars that we know of. In its core, it burns hydrogen into helium and helium into heavier elements, all the way until iron, and starts accumulating iron in its core until the mass of the iron core is so much that it implodes, it just collapses. And at that point, the electrons essentially get pushed into the nucleus and combine with the protons, and that's how you end up with neutrons. And you have a very small, very compact, but heavy, massive object.
Is there some spectacular explosion that the astronomers will see?
Oh, absolutely, absolutely. First, the center collapses, but there are many layers in the star that actually fall on top of this compact object. But since it's so dense, they just bounce right back off and give some of the most spectacular explosions we see, called supernova explosions.
Can we actually see that display on Earth?
Oh, yeah. The most recent one we saw was in 1987. We actually observed it as the supernova was going off. Of course, accounting for the time delay between when it actually happened and when the photons reached us. But in 1987, we saw the photons reaching the Earth, and it's spectacular. And we know of many like this. Here I brought an image of another supernova remnant. This is called Cassiopeia A.
Is that from where it's in the sky in Cassiopeia?
Yes,
Yeah.
it is in that direction. That's right. The remnant of this very energetic explosion at the end of a massive star's lifetime. And this is one of the prettiest ones. It's a very symmetric one. Some of them are not that symmetric. They can go off in certain directions. And this, in fact, is not an image that is taken in the visible wavelength. This is a much higher energy emission. This is in the X-rays. And I don't know if you can see it, but there is a tiny little glowing dot at its center. This is the neutron star remnant that we believe. We believe it's a neutron star. This is the remnant of the explosion.
You said that a neutron star is about as big as Manhattan, the island of Manhattan. Now, if you take an island of Manhattan, you stick it out in outer space, deep space, I'm wagering that's going to be hard to pick up. You know, how do you find such a small, tiny little object out there in the vastness of space?
You're exactly right. Neutron stars are usually good to us in the sense that they send out this unmistakable signal most of the time in the radio waves. In fact, that's how they were discovered. The typical analogy is that of a lighthouse. They have two magnetized hot poles, high magnetic fields, which emit light. And as the star rotates around its axis, we keep seeing this blip of light once every rotation, once or twice every time the star rotates. So this is what's called a radio pulsar, because it emits in the radio wavelength, and it sends extremely periodic pulses that we can pick up with our radio telescopes.
Like a beacon, then. It's a rotating radio beacon
like a
in
beacon.
Space. And
Yes.
and is it really so constant that you can actually time it?
It's the best clock that we know of.
No kidding.